Okay, today we're going to be talking about inscribed angles in a circle. First, I want to be really clear. We're going to just review briefly what a central angle is. So remember, a central angle is an angle at the center of a circle, and we define the measure of an arc to be equal to its central angle. So in this case, the central angle is 50 degrees, which means the measure of the arc, not the length. We'll talk about length in terms of inches or feet later, but its measure in terms of degrees is 50 degrees out of the 360 degree total. If the central angle is 50 degrees, then every single arc from this ray to this ray is 50 degrees, right? It's a 50 degree chunk out of 360 degrees. So again, down here, if an arc has a measure of 100 degrees, then for sure we know its central angle is 100 degrees. Now I say this because I don't want you to get mixed up when we start talking about inscribed angles. Inscribed angles are not equal to the arc they open up to. We call it the intercepted arc. Okay? Instead, they have a different relationship. So central angles are equal to their intercepted arc. All right, so let's start. So our big, huge, super, mega, ultra tricker theorem is that the measure of an inscribed angle, so just like shown here in the picture, an inscribed angle is an angle whose vertex is on the circle. So any angle like that, so notice it's not, the vertex is not in the center of the circle. The vertex is instead on the edge of the circle. So the measure of an inscribed angle is exactly half of the arc. Okay, so if this arc is, let's say 50 degrees, 50 degrees, then its central angle would be 50 degrees. But instead, our new theorem says that the inscribed angle back here, if you pull that vertex further away, the angle gets smaller and smaller until it's half the size, right? And that makes logical sense. If you have an angle like this and you take this point and drag it further away, the new angle is going to be much smaller than that wide angle you started with. So 50 degrees in the center because it's equal to the arc. Pull it back to the circle, and now it's half of the arc is 25 degrees. Okay, so down here I showed you a little picture. One way a student remembered it last year, which I found helpful, is they remembered it was a 2-to-1 ratio, but sometimes they just get caught up multiplying by 2 or dividing by 2. So what they realized is as you went out, the rays went apart. So it got bigger and bigger and bigger. And so they realized that when you go out and you're getting bigger, you multiply by 2. When you're going in and it looks like it's getting smaller, that's when you divide by 2. Now that's not mathematically so correct, and but it's a helpful mnemonic trick just to help you memorize which is which. Okay, but a 2-to-1 ratio. The inscribed angle is half of the intercepted arc. Okay, so let's practice it a couple times, and then we'll look at why it's actually true. So right here, in number 1, let's look at, so we've got a center of the circle, so this is a diameter. That means this is a 180 degree arc down here. So this inscribed angle opens up to an arc of 180 degrees. So if we divide that by 2, we must get a 90 degree right angle. And that's actually going to be one of our tricks we look at today, kind of a consequence of this first theorem. And over here on this next one, we've got 2 different inscribed angles, both opening up to 80. But if this one opens up to an 80 degree arc, dividing it by 2, we know that this angle has to be 40 degrees. But no matter where it is, over here, this one too opens up to the same arc. So dividing by 2, this one's also 40 degrees. So it must be true that 2 inscribed angles that open up to the same arc must be congruent because they're both the arc divided by 2. So the measure of the arc divided by 2 on the right is the same as the same arc divided by 2 on the left. So always 2 inscribed angles that have the same arc are actually congruent. That's actually going to be another consequence. And over here on the right, I just threw another kind of common problem that comes up. So one way to think about this is, since the central angle is 60, that means the arc here is 60 degrees. And then we could say, oh, and now the inscribed angle is divide that by 2, 30 degrees. Okay, another really common trick is, since you know the radiuses of a circle are congruent, you could think about this as not even having a circle and instead just having these three things congruent, and instead you have a triangle. If this is 60 degrees, now if I zoom in, I could say, oh, well, look, so 60 and its linear pair would make 120 degrees over here. And in an isosceles triangle then, I know all these add up to 180 and those base angles are the same. So I go 180 minus 120 and divide it by 2. So I get the remaining x plus x is 60. So if I divide by 2, I get each of those must be 30 and 30. So you could think about it in terms of isosceles triangles too, or you could use your new trick. Okay, so before we go any further, let's look at the y on this one, okay? So I'm going to scroll all the way down here to the bottom. So why is this true, okay? So I just drew a central angle and an inscribed angle here. Let's just draw really quickly a diameter here that goes through our inscribed angle. Oh, that was not a very good one. Let's try that again. I'm going to draw a diameter here that cuts through both of these. That's closer. So now, what do we know? We know we have a bunch of radiuses here. So this one is congruent to this one, is congruent to this one. Okay? So if this part of the inscribed angle is x, well then so is this. So then this must be 180 minus 2x. And then with some algebra, we could see that this has to be 2x here. Or you could have just used your exterior angle theorem to say if you add up two angles of a triangle, they're equal to the inscribed angle. And on the other side, if we do it maybe a different color, we could say, well, this part of the inscribed angle is y, but it's also an isosceles triangle, so this is y. So this angle is 180 minus 2y because it's in a triangle. And then with some algebra, we get that this is 2y. Again, you could just use your exterior angle theorem, say, add up any two angles of a triangle, and that's equal to the exterior angle on the other side. So now look at what we just did. Just using isosceles triangles, we figured out that this angle, x plus y, in relation to this angle, 2x plus 2y, or just rearrange that, that's 2 times x plus y, is exactly half its size. And of course, the central angle here is the same as this arc, so this arc is 2x plus y. This angle is 2x plus y, or 2 in parentheses x plus y. And so for sure, this inscribed angle has to be half that size. Now that didn't take into consideration every case. There's the case like it's over here. It's the same logic. We just use isosceles triangles. That was just one example of how you could walk through a proof that this is true or look at why it's true. This just saves you the steps of cutting it up into a bunch of isosceles triangles. So it shortens the process, and it's a really useful trick. Okay, so let's go back up here. So now that we have that basic idea down, and we've looked at a few examples, let's look at some immediate consequences of that. Okay, one consequence is any two angles inscribed in the, that have the same arc must be congruent, right? So if both of these in their picture open up to AB, well then half of AB is here, half of AB is here, so they must be the same. So I drew in other examples, actually the same example as before. The blue angle, right? It's an inscribed angle here. It's on the circle. It opens up to an 80-degree arc, so it must be, divide that by 2, 40 degrees. And the orange angle also is inscribed and opens up to an 80-degree arc, so it must also be 40. So of course, if they both are half of the arc they open up to, and they open up to the same arc, yeah, then of course they must be congruent. Okay, so that's one immediate consequence. All right, another immediate consequence is half of 180 degrees is 90. So if I have a circle with a diameter, and I draw any angle from the endpoints of the diameter to the circle, so any inscribed angle, it would be opening up to 180 degrees. And so 180 divided by 2 is 90. This must be a right angle. And this is actually useful in real life if you're ever trying to find the center of a circle. And we could talk about that Ooh. Another time. Whoa, bless you. In class. Or bless me. Okay. So, that's the next consequence. I gave you 3 different representations of that. One is, if you have the inscribed angle of a semicircle, you know it's 90. Or the converse of that, if you have a 90-degree angle inscribed in a semicircle, well then multiplying that by 2, you get that the arc it opens up to must be twice as much as 90, or it must be 180, a semicircle. And then the way the book worded it is said, like, what if you happened across a right triangle inside of a circle? Well, if the right angle is inscribed on the circle, then you know it opens up to 180 degrees, and so then you know this AC must be a diameter. So they worded it a little differently, but the same concept. Okay. Now the third consequence is not immediately obvious. Those 2 work, right? We did those 2 examples right away. 180 divided by 2, right angle. Right? Those 2 are both 40 in the second example right here. So yeah, obviously they're the same. The third one's a little more elegant. So first, an inscribed quadrilateral is any 4-sided figure with all 4 vertices on a circle. Right? So then, just like shown in this picture here, it just ends up looking like a 4-sided figure where it's like a laser bouncing off the inside of a circular mirror. So, our theorem is, if a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. Now, don't mix this up, and I'll write this out because this is a common mix-up. Don't mix parallelograms, right? People remember from our previous units that parallelograms, opposite angles are congruent, right? Don't mix that up with this. Opposite angles are supplementary. And by far the most common mistake people make is they just say, oh, opposite angles are congruent whenever it's in a circle, and that's not true. So don't jump to that. And let's look at why the opposite angles must be supplementary, right? So here's a circle. Now we have no idea how big this arc is, and no idea how big the orange arc is. But look at that. Our pink angle opens up to some portion of the circle, right? This pink arc. And then the orange angle, because it's going to the same point on the circle, it must open up to the exact same point, yet in the opposite direction. So it's opening up to the rest of the circle. So we know for sure the orange arc and the pink arc must be 360 degrees, right? And I wrote this out here. So we know these 2 arcs must add up to 360 degrees. And then with some quick algebra, if we know that the inscribed angles are half of that, well then half of the pink plus half of the orange, just factoring out that 1/2, we get half of the, in parentheses, pink plus orange, and we know that the pink arc plus the orange arc is 360, so half of 360 must add up to 180, right? And the simple reason is the 2 arcs, because you end on the same point, just pointed in different directions, the 2 arcs must total 360, and because the 2 angles are half as much, then half of 360 we get 180 degrees must be their sum. Okay, so let's just do a bunch of practice problems now. That's the end of kind of new information. So let's do some problems here. Okay, so it wants us to find the measure of angle G here. So we would look at this and we'd say, okay, well, we have a whole circle of 360. So we could find out this remaining portion by 360 minus 70 minus 120. We get that we have a 170 degree arc here. And so then the measure of angle G, which is an inscribed angle, must be half of that. So we get 85 degrees in here because that's half of 170. Okay. Very similar on number 5 is we have a diameter cutting this into 180 degrees and 180 degrees. So to find LM, we just do 180 minus 160. And so we say, oh, there's 20 degrees left over on this half of the circle. So arc LM must be 20. And so the measure of angle N, which is half of the measure of that arc, right? It's the arc divided by 2. So the measure of angle N is 1/2 of 20, or 10 degrees. Okay? Right, so let's go to another example here. Now we're looking at an inscribed quadrilateral, so what do we know? Now again, the common mistake is to say, oh, I remember that opposite angles are congruent. Now, if this is true, we could prove that this is a parallelogram. In fact, that was one of our properties, that if that was true, it means the shape is a parallelogram. So do not assume these to be true, not necessarily true. What we do know is that since angle G opens up to this, we can even figure it out. This must be 120, right? 60 times 2. And then we know angle M opens up to the rest. We'd say, okay, well, 360 minus 120, that's 240 degrees. We must divide that by 2 to get the inscribed angle. So that's 120 degrees is M, right? So we could have done it the long way, but our shortcut is that opposite angles are supplementary. And so we could have just said M plus 60 equals 180 and 2K plus 60 equals 180. And so we get minus 60 minus 60. We get that M equals, 120 degrees. And that, with some algebra over here, 2K is 120. And so K must be 60 degrees. Okay, and again, it's opposite angles are supplementary if it's an inscribed quadrilateral. All right, so this one says in each star below, all of the inscribed angles are congruent. So there's 5 congruent angles. And look, it opens up to this piece. The next angle opens up to this piece. And so it's 1, 2, 3, 4, 5 congruent arcs. So we take 360 total degrees, divide by 5, and get that each of those arcs is 72 degrees. Okay, so if each of the arcs is 72 degrees, well then we just take that and divide it by 2, and 72 divided by 2 would be 36 degrees for each angle. Right, and do the same thing for B and C for that one. Just different numbers instead of 5. Okay, and one more on this, then we'll jump over to IXL. So here it says we have a parallelogram inscribed in a circle. So we know when it's a parallelogram that opposite angles are congruent. Okay, but we also know quadrilateral inscribed in a circle is opposite angles are supplementary. And so if 2 angles are both congruent and supplementary, that means 2 things that are the same add up to 180 degrees. So that must mean the angles are 90 degrees. Right? That's the only way for 2 numbers to be the same and add up to 180. And so it doesn't ask us, it just says find the angle. So all 4 angles are 90 degrees. So what shape is this? So what we just figured out is that every single parallelogram that's inscribed in a circle must at least be a rectangle. This wasn't part of the question, but that's an interesting deduction. So if you place a parallelogram in a circle, it must be a rectangle. Could be a square maybe, but at least it must be a rectangle. All right, so let's do a couple IXL problems now. If you feel like you're ready, awesome, move on. If not, stick with me. All right, so here we go. In this one, it says what's SRT. So coming out here, we know the central angle is 70, which means this arc is 70 degrees. And so the inscribed angle then, we would divide that by 2, and we get half of 70 or 35 degrees. Okay, so this one, very similar, I think, RST. So yeah, this one's 66. Oops. 66 means 66 up here. To get the inscribed angle, we would divide that by 2. We get 33 degrees. So this one's a little different. We did an example like this in class. We got 2 different approaches here. One is we say, okay, let's look at arcs or angles. But either way, we've got a diameter creating 180 degrees. So 180 minus 115, we get 65 degrees over here, which means 65 here. So you could have done a 180 degree angle or a 180 degree arc to get that either way. So if we want to look for angle TUV here, what we're really looking for is half of that. So we'd get 65 divided by 2, or 32.5. Now I'm going to show you an alternate way to do that same thing. Okay, so let's clean this up a little bit. So another way to do that same thing is not use this shortcut that we have, although I for sure would. I would get really comfortable with it. But another way is, since all radiuses are the same, we have an isosceles triangle here. So to figure out these two angles, we could say 180 minus 115 divided by 2, or 65 divided by 2, or 32.5. So you get the exact same numerical steps, the same answer, but a totally different logical flow. One is dealing with an isosceles triangle because radiuses are congruent, and the other is using central angle is equal to arc, and then the inscribed angle is half of that. Either way, we end up getting 32.5 degrees. Ooh, different. Okay, so let's look at this one. We're looking for SUT. So again, we've got the same situation where I could use isosceles triangles to find these two angles, isosceles triangles to find these two angles, and then I could add these together. However, rather than doing that, I'm going to instead look at arcs and angles. So looking at these angles in the middle, I know there's a total of 360. So I'll take away the 154 and the 125. And I'll get, ooh, that's 206 minus 125. So that's that's 81, I believe. Yeah. So 81 is here. That means this is an 81 degree arc because its central angle is 81 degrees. And that would mean that then the inscribed angle would have to be half of that. So this total angle here would be 81 divided by 2, or 40.5 degrees. Ooh, a right angle. Let's see. What is measure of RTS? We have a right angle here, which is 90. It means this is a 90 degree arc, because that's the central angle. And so this angle here is half of that. So RTS is 45 degrees. A really common mistake is people not following that system of logic, and it's like kind of arbitrarily multiplying by 2 or dividing by 2. Oops. Okay, so let's try a few more. So we've done this one before, so we're looking for angle QSR. We're looking for this angle here. So again, I'm going to subtract from 180. I'll get that this one is 81. I'll get that means this is 81. And half of that is, oh, we've even had this number before, 40.5. All right, so now all of them are kind of getting the same, but hopefully you get the idea and you can go ahead and use this on your own. Good luck.